cesium ytterbium. There is some advantages. Cesium ytterbium have electronic dipole moment and magnetic dipole moment. And with this turnable electronic dipole, electromagnetic dipole interactions is very significant for research in the quantum simulations, precision measurement, and the explanation for the new well quantum phase. And more motivations like magnetic association followed by T-hub is a promising road to create the ultracold ground state molecules. But currently, the research on cesium ytterbium is mainly focused on the ground state. However, the feedback resonance in the ground state is typically very narrow. So to overcome these limitations, we turn on our attention to the miscible ytterbium in the triplet p state, which should offer modern feedback resonance. Therefore, the electronic structure of cesium ytterbium in the excited states must be modeled. And as we showed, I summarized all the dissolution limit for cesium ytterbium, and there is some special structures. For cesium in the 7s state, excited state, is in the middle of ytterbium in the miscible triplet p state. It's very special. And this work is collaborated with Durham team. And I will show our result for how we calculate the potential energy curves. Collaborate with our colleague Zonghan Yu. We use the CsYb to calculate the PECs in HondKSA. Basically, our model is use three effective valence electrons moving in the field of extended by two polarizable ionic cores, ytterbium 2+ and cesium+. And the core interaction and valence core interactions are described by modern potential. And then we do full CI calculations for these covalent valence electrons interactions. And And actually, we have do some similar things for the 3-electron system with rubidium strontium. So we trust our model is effect here. And in the right side, we show our computed cesium ytterbium potential curves. And but compared with the rubidium strontium, there are some limitations because ytterbium in the miscible state, if higher it, the Fourier shell gonna open, so the CsYb calculation can not be very work well. Okay, so the next step, let's think about the spin-orbit coupling. So we use Clash-Gordon coefficient to transfer to the HondKSA, and we add a model, add a atomic model of spin-orbit coupling in our Hamiltonian. I know that is not very useful for the short range, but at least we have a try to see what happened. And for me right now, I was yes, the omega is a total is a projection of the total angular momentum. For the each asymptote for cesium in the 6p state, cesium in the 5d state, and ytterbium in the triplet p state, we have the spin-orbit matrix like here, and the spin-orbit constant we driving from NIST database. These are independent, but let's have a try. Okay, let's see what happened. Here is our result for the HondKSA in our model. The electronic state is like this, and yes, everything goes well. But we mentioned for cesium in the 7s state, the dissolution limit is in the middle of miscible ytterbium state. So in our atomic model, there is a crossing between each other, so which is not very adiabatic. So it's have some limitations in our model. But yes, we maybe for the next step we can deal with it. But right now, let's just have a look what happened here. And also for in our model, we do long range interaction calculations. It's mainly about the C6 coefficient. In order to calculate the C6 coefficient for every electronic state, we have to find the anisotropic and isotropic C6 coefficient, and we use polarizability in emitter frequency to calculate this, and we use the energies and transition moment to get this polarizability. But for CDM part, we have some tables and some literature, so it's very easy. But for ytterbium, it's not so easy. And we found some reference about the oscillator strength in real frequency. So when the omega equals 0, the immediate frequency and the real frequency should be the same. So there is some link, so we can transfer from the transition dipole moment to the oscillator strength. And we use these oscillator strings from those reference to get these static polarizabilities, and compared with some measurement values in the experimental reference, and we found that for the ytterbium in the ground state, we are in the safe side, and then we get the right C6 coefficient, which is very reliable. And we do all the calculations with the triplet B state. And then we get the table for the calculation C6 part, and we have the potential energy curves in the short range. Beyond the Lorry radius, we do a fittings, use the C6 and C8. Like for every electronic state above the Lorry radius, we get the C8 coefficient, and then we get the full potential energy curves. So what's the next step? There is already some previous reference published before is here, and we want to do a comparison. The dashed line is from their conference, and the soil line is our calculation result, and the same color in the same figures mean the same state. What we found, like in the ground state and the CDM in the 6p state, the wave depth is so different. You can see a huge difference here, and also in their in this reference, they do a fitting, use a C3 coefficient, which is wrong for the CDM ytterbium. It should be second order dipole-dipole interactions. And also for the CDM in the higher excited state, like for the 5D state, there's two state doublet delta state calculation, this state missing in their calculations, and also you can find their huge difference for the dissociation limit. And for the misstable ytterbium state is more worse. You can see the color not compared with each other, which means there is some long labeling in their calculation. So it's strange, but it doesn't mean that we do better than them. So what should I do? Do another comparison. So I found another reference from Durham's team fitting on the measured bonding energies of near shared rod vibrational levels, and we found that in the short range we have almost the same wave depths and equivalent distance. It's good, and for the C6 coefficient, their fitting values is constant with our calculation values, which is also good. And we have our own potential curves to do to get the vibrational levels, and we do a comparison between the observed numbers and our calculation numbers. Actually, it have some different, but it consists with each other. So we trust our excited state is better than the previous one. So as a conclusion, we have calculated the potential energy curves in HONG-KSA and HONG-CSA for all the excited state with dissociation limit lower than the ground CDM state and misstable ytterbium state. Our calculations are consistent with model fitting the experiment result in the ground state, and we have performed all reliable calculations in the excited state. But as I said, is for the spin-Albert coupling is atomic model. It's have so many limitations. So the spin-Albert coupling constant are independent. It can be a mess, and it's due to this R independent spin-Albert constant. there is some couplings, there is some crossings in the CZM in the 7s ytterbium 6s2 state between this dissociation limit. So my next step is like to develop my models. We can calculate can we calculate the spin orbit dependent R dependent spin orbit coupling constant. In principle, yes, we have done the same things for the 2-electron system, but the 3-electron system is more hard. And then maybe after doing this, I will calculate some phase bulk resonance in this ytterbium in the miscible state and try to find some effective step. So thanks for my supervisors, Olivier Duluvier and Nadia Bafaloma, and also my colleague, Homa Mixu. Thanks.
Thank you very much, Zonghan.
Thank you.
We have a question for Zonghan.
Very interesting result. And notice by your calculation, there are certain combination you have a negative C6 and some with a negative C8.
Yes.
Can you comment on this? I didn't see anything both negative C6 and C8. Comment on how under what condition you get negative values.
Actually, as I mentioned here, we use this transition dipole moment to calculate the C6, and we get the anisotropic and anisotropic C6 coefficient, and just like doing things like here. But actually, there is some. Sorry. For this. Actually, I know little about these things because there is very few reference there. Some of them are positive, some of them are negative, and it depends on the method you used. So right for this part, I don't know.
Okay, thank you. There's one more question by Jeremy.
Maybe just comment on the first question before I move on to my own one. I mean, you can quite easily get C6 coefficients of the opposite sign if the dispersion interaction is dominated by interactions with a state that's below you rather than the state that's above you, and that's fairly common in excited states. So I haven't looked at the details of this, but I don't think I'm immediately worried by it. My question though was, you mentioned that in your model the cesium 7s state is in the middle of the ytterbium triplet P state.
Yes.
Where should it be?
This data is from NIST database. It should be there, and in our calculation, it is here, but it have some influence in the short range potential energy curves.
So sorry, I'm trying to see that.
Yes, here.
So it should be just about 600, 500 wave numbers above the triplet P1. And where is this in your picture? I mean, sorry, how far different from this is yours?
Actually here, yes, actually here we just do a shift there, because in our calculations there is only 20 wave numbers in our calculations. It's due to ytterbium have 2 electrons there, so our calculation have some issues in the dissociation limit for ytterbium.
But if you don't do a shift, where is it compared to where it should be? That's
okay, sorry.
Are those numbers from NIST or from your calculation?
Yes,
without any
it's
shift?
from NIST for the dissociation limit.
Okay,
In our calculation, it should above this. Sorry, where is it? 7s. These two difference is about 20 wave numbers in our calculation.
Okay,
Yes.
so it's only 20 wave numbers out of 500. Okay, that's fine. So this crossing between the two states is basically physical. It may be slightly wrong, but it's really there and really fairly close to where you get it.
Actually, I guess it's our model limit. If we use some R-dependent spin Albert constant, and there shouldn't be a crossing here. There is a void crossing there. Oh, sorry.
Okay, maybe we need to talk about this.
Yeah,
Thanks.
yeah. Okay,
Thank you,
thanks.
Jeremy. Maybe it's just a quick question. So did you even look at maybe Franconin factors as well? Because this reminds me a bit of calcium fluoride as well. So you might be able to even directly cycle some photons in the molecule directly, right? If I look at the doublet sigma to doublet sigma transition, for example, did you look into this?
In our CsYb calculation, we considered the transitions between the different dissociation limit.
So I mean, you know, like, so you could maybe now you don't have to dissociate the molecule anymore, but maybe
yes.
directly excite the molecule and actually scatter a few photons here.
Yes.
Yeah.
I'm sorry. I'm sorry.
Don't worry. All right. Let's thank Zonghan once more and then move on.